There was a moment in Earth's history when the world did not explode in an instant, but died slowly. Not a meteor wiping out the dinosaurs, not a sudden cosmic blast, but a long, grinding chain of upheavals lasting hundreds of thousands of years, long enough to break every ecosystem and violent enough to nearly erase all life. This moment is known to scientists as the Great Dying, the Permian Triassic mass extinction, when 96% of marine life and over 70% of land species vanished. What could drive a thriving planet to collapse so completely? And why was Earth fortunate enough to avoid becoming a dead world like Venus? This journey will take you back 252 million years to the day life hit rock bottom. Before everything fell apart, Earth at the end of the Permian was a world both familiar and alien to us. Most continents were joined into a single supercontinent called Pangaea, a landmass so vast that even walking your entire life might not get you from its eastern edge to its western shore. But that immensity made the climate extreme. Much of the land lay deep inland, far from the ocean, making the air dry, summers blisteringly hot, winters freezing cold, and rainfall so rare that only a few storms fell each year. Harsh as it was, Pangaea's ecosystem still endured. The creatures of this era looked nothing like the famous dinosaurs or mammals that would come later. Instead, the world belonged to strange beings that sat at the crossroads between reptiles and mammals. On the dry plains roamed dicynodonts, stocky animals with turtle-like beaks, long tusks, and some of the most successful plant eaters of the Permian. Around them lurked the terrifying predators of the time, gorgonopsids with massive skulls and dagger-long saber teeth. Though not gigantic, they were the true rulers of the land, swift, agile, and perfectly adapted to the unforgiving climate. Farther north in Pangaea lived Scutosaurus herds, large, heavily armored creatures moving together to avoid heat and predators. Plants were equally unusual. Ancient conifer forests, giant ferns, and drought-adapted shrubs dominated the landscape. Meanwhile, the Permian oceans told a completely different story. Beneath the deep blue waters thrived a world of ancient corals, mollusks, primitive bony fish, ammonites, and thousands of tiny organisms forming dense ecological webs. The coral reefs of the Permian were among the largest living structures ever to exist on Earth, providing shelter and food for countless species. Yet this seemingly stable world was already stretched to its limits. Some regions had begun experiencing droughts lasting longer than usual. In a few places, strange signals in sediments showed slight changes in ocean temperature and salinity. Still, these were only scattered anomalies, nothing that any living creature could interpret as the first faint warnings of an unprecedented catastrophe. Life in the Permian had adapted well to harshness, but it was not prepared for what was coming. Because within just a few 100,000 years, a blink on the geological timescale, the dry heat of Pangaea would turn into a planet-scorching inferno. And the cause did not come from outer space, but from beneath their feet. Around 252 million years ago, deep within Earth, an enormous volume of magma began rising from the mantle. This event was unlike any volcanic activity we have ever witnessed in modern times. This was not a single volcano, but an entire volcanic province, so vast that it covered an area larger than Europe. For hundreds of thousands of years, magma kept rising through enormous fissures in the ground, forming lava layers tens of meters thick, stacked one atop another in repeated pulses. To grasp the scale, if humans had lived at that time, even from thousands of kilometers away, they would still have seen the sky glowing red at night, not from forest fires, but from gigantic lava lakes blazing across the horizon. Ash from the continuous eruptions was carried by winds across Pangaea, shrouding many regions in a gray haze for years. But ash was only the beginning. The real danger lay in what the eruptions released: massive amounts of carbon dioxide and sulfur dioxide. Modern calculations estimate that the total carbon dioxide emitted from the Siberian traps was equivalent to thousands of years of all human emissions combined. Not only that, as magma spread through carbon-rich and methane-rich sediment layers, it heated and released vast quantities of methane, amplifying the greenhouse effect exponentially. Methane is roughly 80 times stronger than carbon dioxide over short timescales, so this combination was enough to turn Pangaea's climate into a nightmare. Some modern studies even suggest that rising magma may have ignited natural carbon reserves in ancient coal and petroleum deposits. This remains a hypothesis, but it fits the unstable carbon signatures found in rock layers from that time. If true, it would mean Earth during the Permian was hit with multiple sources of toxic gases and greenhouse gases at once, a scenario capable of triggering uncontrollable climate change. Climate change began slowly, almost imperceptibly. Dry seasons lasted longer, and rainfall became unpredictable. But over time, these disturbances did not stop. They intensified, like a crack in ice widening day by day. Global temperatures rose little by little, but steadily, with no sign of stopping. As magma continued to erupt, atmospheric carbon dioxide levels climbed beyond anything life had ever experienced. The oceans began absorbing this carbon dioxide, causing seawater to acidify. No creature on the beach could see it happen. But beneath the waves, coral reefs, the foundation of marine ecosystems, began to weaken. That weakening would become a critical part of the cascade leading to mass extinction, but for now, life still held on. The peak of the Siberian traps may have lasted hundreds of thousands of years, according to geological evidence. This means Earth did not face a single catastrophic blow, but a relentless series of impacts, never allowing ecosystems a moment to recover. The crisis had not yet reached its worst point. The glowing lava fields of Siberia were only the opening act. When enough toxic gases accumulated, and when the oceans began reacting to extreme shifts in temperature and chemistry, life on Earth would enter a phase of complete collapse. A collapse reflected most clearly in the violent transformation of the climate. And that is the focus of the next part, when the air, the land, and the sea all became enemies of every living creature. The prolonged eruptions of the Siberian traps blanketed the sky with ash and pushed Earth to the brink. The surge of carbon dioxide and methane drove planetary warming at a rate never seen before. At first, the climate changed only slightly, hotter, drier, with irregular rains. But within just tens of thousands of years, a brief instant in geological time, global temperatures had risen 10 to 15 degrees Celsius, far beyond what most species could withstand. The equatorial regions turned arid, with deserts expanding and swallowing forests and wetlands, the lifelines of herbivores. The food chain collapsed. Scutosaurus, Dicynodonts, and then Gorgonopsids disappeared one after another. Herds of animals migrated desperately across cracked landscapes, while rainfall became increasingly rare and erratic. All of Pangaea fell into a state of burning forests, dry rivers, and fractured plains. At the poles, permafrost melted, reducing Earth's ability to reflect sunlight and causing the planet to absorb more heat, a positive feedback loop that accelerated climate change. Oxygen isotope analysis in marine sediments shows that warming penetrated deep into the oceans. The seawater did not boil, but it warmed enough to disrupt chemical and biological balance, causing mass marine die-offs. As plants and animals died in vast numbers, decomposition and wildfires released even more carbon, intensifying the warming. Ecosystems fell into a self-amplifying spiral. Death produced greenhouse gases, and greenhouse gases produced more death. Along coastal regions, algae bloomed excessively. When they died, decomposing bacteria consumed all available oxygen, forming dead zones, where almost no multicellular life survived. When the oceans, the heart of life, lost their regulatory power, Earth entered a state of full-scale crisis. Dead seas expanded, the atmosphere grew suffocating, and ecosystems collapsed from the ocean floor to the continents. The Great Dying was not just climate change. It was the global transformation of Earth into a toxic environment where nearly all forms of life were erased. In every mass extinction, the oceans suffer the most. But in the Great Dying, the oceans were not merely damaged. They collapsed entirely, becoming the primary driver of the Permian Triassic extinction. As the climate warmed, carbon dioxide in the atmosphere surged. The oceans absorbed much of this gas, causing rapid acidification. The sudden drop in pH killed vast numbers of organisms dependent on calcium carbonate, such as corals, mollusks, and shelled creatures. Coral reefs bleached and crumbled, like the foundations of the entire marine ecosystem giving way. Small fish lost their shelter, leading larger fish and ancient marine reptiles to vanish, a domino effect across the entire food chain. At the same time, dissolved oxygen in the water plummeted. Warmer water holds less oxygen, slowing circulation between surface and deep layers and creating dead waters where only anaerobic bacteria could survive. Evidence comes from pyrite-rich rock layers, minerals that form under low oxygen conditions, found worldwide indicating global anoxia. As the environment became anaerobic bacteria proliferated, producing hydrogen sulfide, a toxic gas with a rotten egg smell, deadly to multicellular organisms. Normally, hydrogen sulfide is oxidized, but when the oceans lost oxygen, the gas accumulated uncontrollably, turning waters green or purple depending on the bacterial species. Organic pigment-rich sediments show that photosynthetic anaerobic bacteria once dominated, proving that the oceans had transformed into toxic seas. As hydrogen sulfide concentrations continued to rise, the gas escaped into the atmosphere, forming a poisonous layer of air over coastal regions. At high levels, it causes nervous system paralysis and kills animals within minutes. Coastal life, from fish to reptiles to insects, was wiped out. Atmospheric studies indicate that hydrogen sulfide could even destroy the ozone layer if it reached sufficient concentrations. Fossil evidence shows that UV radiation spiked dramatically, causing DNA mutations in plants and triggering the collapse of entire forests, which in turn brought down the terrestrial food chain. In the open oceans, life also faded away. Ancient fish, mollusks, and crustaceans all vanished from the fossil record, leaving no descendants. On the seafloor, only black, oxygen-poor mud remained, filled with countless carcasses sinking to the bottom. This phenomenon lasted thousands of years, creating a state of global euxenia. Oceans filled with hydrogen sulfide and nearly devoid of oxygen. Some studies suggest that this euxenia may have reached even the open oceans, not just coastal zones. The entire marine biosphere, once the biological core of the planet, collapsed completely. From the deepest depths to the sunlit surface, few species could survive the lethal combination of high temperatures, low oxygen, and toxic gases. When the oceans, which supply roughly half of Earth's atmospheric oxygen, became paralyzed, terrestrial ecosystems also plunged into crisis. Yet amid catastrophe, a few small organisms survived. Bacteria, simple life forms, and some fish and crustaceans hiding deep in mud layers or in frigid polar waters. They were not the strongest, but they were the best adapted. These seemingly insignificant organisms became the foundation for Earth's recovery after the planet nearly turned into a dead world. As the oceans grew toxic and the continents turned into endless, burnt-out wastelands, most life on Earth fell into silence. Yet even in this darkest moment, some organisms not only survived, but endured the prolonged devastation. They were not the strongest, nor the smartest, but they possessed traits that allowed them to withstand the collapse of the entire planet. Most notable among them was Lystrosaurus, a stocky creature roughly the size of a wild boar, with a tough beak and strong limbs built for digging. In the fossil record, Lystrosaurus makes up 70 to 90% of all terrestrial vertebrate fossils immediately after the mass extinction, a number that is astonishing in itself. Their dominance didn't come from superior evolution, but because they were among the few species whose lifestyle perfectly matched the chaotic conditions of the early Triassic. The greatest strength of Lystrosaurus was its burrowing ability. As the climate became extreme, the air filled with toxins and temperatures surged. They could retreat into underground burrows where temperatures were more stable, humidity was higher, and exposure to UV radiation was reduced. These burrows became natural shelters against the weakened ozone layer and the hydrogen sulfide drifting inland from the oceans. Moreover, Lystrosaurus were simple herbivores, primarily chewing roots and tough vegetation. When forests and complex plant ecosystems vanished, species dependent on diverse food sources disappeared, while Lystrosaurus continued to exploit whatever plant matter remained underground. Beyond Lystrosaurus, several smaller but equally resilient species survived. Many insects and small amphibians had short life cycles and rapid reproductive rates, allowing them to adapt across generations. These species could cope with sudden environmental shifts far better than large animals, which required longer times to adapt. Some small fish living in deep water or isolated inland lakes, less affected by euxenia, may also have survived the worst phases. Species adapted to low oxygen environments naturally had an advantage. Some ancient fish and amphibians could absorb oxygen through their skin or lived in stagnant, oxygen-poor waters. These groups were already accustomed to shallow, low-oxygen environments, so the ocean-wide oxygen crash affected them less severely. One shared trait among many survivors was small body size. During times of resource scarcity, large species typically required more food and therefore had a higher risk of starvation. Meanwhile, small organisms consumed far less energy, could survive on minimal food sources, and could move more easily to find suitable environments. This explains why, after the extinction event, the world became dominated by small organisms rather than the gigantic species that had previously ruled. The role of ecological luck cannot be ignored either. Some species may have happened to live in areas less affected by toxic gases or near the few remaining sources of clean water. This was not due to superior ability, but simply because their geographical location allowed them to avoid the worst impacts of the catastrophe. These survivors, small and unremarkable compared to the magnificent species that vanished, nonetheless carried the seeds of Earth's recovery. From these surviving groups, over the millions of years that followed, ecosystems would slowly rebuild from nearly nothing. Yet this revival did not happen quickly. It took nearly 10 million years for life to regain stability, and many tens of millions more to evolve into a completely new world. A world that would eventually give rise to even more famous giants, the dinosaurs. And that long, arduous rebirth is the focus of the next chapter. How did Earth recover from its own near death? After the extinction storm passed, Earth did not immediately return to equilibrium. Instead, the planet entered a prolonged period of chaos, where the environment remained unstable and life clung to whatever remnants it could find. The period immediately following the Permian Triassic event was not a moment of rebirth, but more like a long post-shock phase lasting millions of years. In the early Triassic, the climate remained hot, the land barren, and atmospheric oxygen far lower than before the catastrophe. Many parts of the ocean still suffered from low oxygen or high concentrations of hydrogen sulfide, making marine recovery painfully slow. Yet life persistently reopened small doors. Survivors like Lystrosaurus began expanding their range, because with few natural competitors and fewer predators, they had more opportunities to multiply. In fact, early Triassic fossils show an almost overwhelming abundance of Lystrosaurus, indicating the occupied regions that many species once competed over. This is a classic example of an ecological phenomenon known as faunal turnover, when an older animal community is almost entirely replaced by a new group after a mass extinction. In the oceans, recovery happened more slowly but steadily. As the volcanic activity of the Siberian traps weakened, the amount of carbon dioxide released into the atmosphere decreased. Earth began a long self-balancing process. Weathering of rocks on land absorbed carbon dioxide, the oceans gradually dissolved excess greenhouse gases, and the atmosphere slowly stabilized. Although this was a slow natural process, it helped reduce the greenhouse effect and allowed global temperatures to gradually fall. As temperatures declined, oceanic circulation slowly recovered. Oxygen began returning to deeper waters, pushing back the state of euxenia. Many plankton species reappeared first, tiny organisms that formed the foundation of the entire marine food web. Their return paved the way for the recovery of invertebrates, small fish, and eventually larger species. On land, plants were slow to recover, but equally vital. At first, ferns and drought-tolerant plants were the groups that rebounded the fastest. They did not require nutrient-rich environments and could grow even on the depleted soils left behind after the catastrophe. As vegetation expanded, the oxygen levels in the air gradually increased, providing more favorable conditions for vertebrates to develop. Around 5 to 10 million years after the Permian Triassic event, Earth began to show a clearly improved level of biodiversity. New groups of animals appeared or expanded rapidly, most notably the primitive-looking reptiles, distant ancestors that would eventually give rise to dinosaurs. This was the moment when new ecosystems were formed, vastly different from those that existed before the mass extinction. Fossils from this stage show organisms with lighter body builds, longer legs, faster running abilities, and more efficient metabolisms. These changes are thought to be an evolutionary response to the hot and unstable Triassic climate. It is one of the clearest examples demonstrating that mass extinction does not only erase life, it also reshapes the entire evolutionary direction of the survivors. And then, around 20 to 30 million years after the mass extinction, a new group of organisms appeared and quickly dominated the environment: dinosaurs. They were not remnants of the Permian era, but distant descendants of the small surviving groups that were allowed to flourish in a world without their former competitors. Without the Great Dying, the post-Permian fauna might have followed a completely different evolutionary path, and dinosaurs might never have ruled the planet for more than 160 million years. Earth's recovery after the greatest mass extinction in history did not happen in a moment, but stretched across tens of millions of years. Yet it is precisely this long, grueling process that shows the extraordinary resilience of life, a system that can be nearly annihilated and still find a way to rise again. And that also forms the perfect foundation for the final section, an open-ended conclusion, non-didactic, but clarifying the scientific meaning of the Great Dying and what it reminds us about the present. The Permian Triassic mass extinction was not only a dark milestone in the history of life, it is also evidence that a planet can be pushed to its limits solely by prolonged changes in climate and oceans. Without the Great Dying, dinosaurs would not have emerged, mammals would not have risen, and humans might never have existed. When scientists look back at this event, they do not seek moral lessons. They investigate the mechanisms that once caused Earth to collapse and assess whether those mechanisms could repeat in the future. What remains after everything is a single, open, scientific question: what will determine the next major transformation of this planet?